Okay, good morning, everyone. Today we'll discuss one of the most important things in the world. Actually, what is it? Relations. Actually, that's one of the most important things. Actually, we deal with it every day, relation between people. All right. So technical term is called binary relations. That's the most fundamental one. Of course, we can talk about relations not only between two objects, but between among many objects. We'll touch that one later, okay? But the foundation is really binary relations. It's a connection between two types of objects. All right. So here is an example of a binary relation. It's a relation from students to courses. So here, this are relation. Describe a relation from students so that's a set of objects, all right, to courses. So which is specified by this table. So in the column, we have list of students. Here we have list of courses. So these are loads of different loads in this column, okay? Now, if a student, say Alice, obtain A grade from a particular course, we pick it. So this indicates Alice have received grade A for all three courses, and Charles got A from these two courses, and so on. So that's a relation. So that's given a connection between students and the courses in terms of whether students obtain grade A. All right. So that's one way to represent it, use a table representation. But it will be easier actually to use a graphic representation. So here one side is set students. So that's a set of students. The side is set of course. So these are all courses. And if student S obtain a grade A from a particular course C, then we draw an arrow from student S to C. So for example, for Alice, you can see we have these three arrows go to these three courses. And Charles, only two, and Bob, only first one and second one. All right. So that's very good for actually for illustration purpose or for teaching purpose because it's graphic. It's easy to see what's going on. And now for actual manipulation of relations, the best way, I can't say the best way, or more convenient method, the best way maybe, is to use a matrix, use a zero matrix to represent relation. So for this relation, we have an associated matrix, MR, where each row represents a member inside A. So here were students. So corresponding to these three students, we have three rows, first, second, and third. And each column corresponding to courses. So we have three courses. Okay, then the correspondence is obvious. Instead of pick it, we use one if student S obtain grade A for course C, and zero otherwise. So that's given as a matrix. Later on, we'll see it's very easier to do operation on relation if we use matrix representation. All right. Okay. Sorry, I disabled the public chatting for private chatting. Okay. Let's see. I have this gadget to see if I can see it. All right. Is it big enough? Let me check. Maybe. This not a valid question. Okay, I just joking. Okay. I see some chatting to see if there are questions. Please don't ask this type of question during class. If you have something don't understand about the course, you can use chat to ask. But otherwise, please ask me later other things. Okay, because I cannot just keep on interrupting and come to you because I see other things. All right. Okay. So that's the basic idea of a relation. Now we are going to define them mathematically. All right. A binary relation that's a connection between objects in two sets. So typically, we will not say binary, so just say relation. All right. So we describe the relation to relate elements inside A to elements inside B. So basically, what we do is relate some relate an element, a particular element inside A to some elements in B. So that's the purpose of relation. We try to relate an element for each element. Maybe I better, yes, that's okay. I mean an arbitrary element. Relate an element A to some element B. So here, actually a subset of B. So that means. So that's the purpose of relation. We establish a connection for an element inside A to relate to several elements of B. So that's the purpose of relation. So related. All right. So mathematically, how we define it, we're using Cartesian product to define it. So given two sets, their Cartesian product is the ordered pair, where first element comes from A, second element comes from B. I'll give you an example. Right. Suppose A is AB and B contains 1, 2, 3. Then Cartesian product of A and B. How many elements? 2 times 3, 6 elements. All right, so it's Cartesian product of A and B. So each element is an ordered pair. First element comes from A, second element comes from B. It's very important, it's ordered. So that means B times A is typically quite different from A times B. So in this case, number of elements is same, but the value is different. So here will be 1A, 1B, I call it 2B, 3B, 3A, fine. So, and here 1B, 2B, 3B. Okay, so that's packaging product. All right. So formal definition, mathematical definition of relation is just a subset of packaging product of A and B. So that means each element is a pair where first one comes from A, second one comes from B. So for example, for this example, suppose it's B1, B2, B3, say B4. So after this one is 4 pairs, A, B1, A, B2, A, B3, and A, B4. That tells us A is related to B1, B2, B3, and B4. Okay, so that's formal definition of relation. It's a subset of Cartesian product. So each element of relation is the ordered pair, where first element comes from A, second element comes from B. So a relation is a set. R is itself is a set. So it's very important, this concept, very basic concept. All right. Now, relation is a generalization of functions. The relation is generalization of function. A function is a relation. It's a very special relation. In a function, an element is matched to one element on B side. But a relation allows us to map to many elements on B side. So it's a generalization. Actually, one can use a function to specify relation. Now, the function from set A to B. Okay. Now, relation can be described by function. If we use terminology of function, we can also use it to describe a relation, but it's better to describe it in this way. The way to describe it is for relation, actually it's a function from A. Now here it's to a power set of B. That's the relation. Relation can be regarded as a function. It maps each element of A to a subset of B. To some element of B is a subset of B. So this, the range part, full domain, is a power set of B, all possible subsets. All right. The relation can be also viewed as a function, but it's more convenient to view it in this way. It's a subset of Cartesian product. It consists of a collection of pairs of elements. Okay. Is that clear? The notion of relation. Okay. Now I give you a lot of examples about relations. Okay. So notationally, when we say A, B belong to R, because R is a subset, relation is a subset. All right. So using notation for set, the A, B is a member of R. We write in this way, but conventionally, very often, we use index notation. We put R between A and B. Very often, we do it in this way instead of this way. Conventionally, we'll do it in this way. Actually, seen it very often in practice. For example, A divides B. A divides B. It's a relation. So this one is a relation. So this one, relation from positive integers to positive integers. So whether integer A divides B or not. If it's A divides B, then it's here. We put one there in the matrix. Then it will belong to this relation. Okay. So in other words, this one, if only if this pair belongs to this relation. If we regard this one as a relation. So this notation same as this notation. But you see, it's more pleasant to reading this way instead of this way. That's why very often you use index notation. Okay. Now some common examples. For example, child-parent relation, people-edge relation, relations of occupation. All right. So here, relation is P to P. So it's a subset of product, Cartesian product P to P. P denotes people. Okay. So P denotes people, set of people. And people edge, so here P to positive integers, for example. All right. Then for numbers, we have this very actually a lot of common relations. Equality relation, less than relation, less than or equal relation. These are common relations we see. Say we usually write say 3 less than 4. We don't write the 3, 4 belong to this relation. Normally we don't write it this way. Rather we write it this way. So that's why very often we use infix notation. Okay, so that's common relation. Less than or equal than, or equality. Okay. Also the subset relation. The subset relation for set. So that's a universal set. So it's universe is U. So all objects touching with under this one, or you say interpret as domain. So then the subset. So these are relations. Okay. So now you should have a very good feeling about what relation we mean. What we mean by relation. All right. So let's see. So representation I mentioned very often we use graphic representation or matrix representation. And as I said, matrix representation will be very helpful. Okay. All right. Of course, in practice, relation we deal with may not be only binary. We deal with multiple relations or k-array relations. Okay, so we can deal with relation involve more than 2 objects. So for example, we can have A, B, C. The student may be Alice. The course may be ENGG. The course 2440, and the grade may be get an A. So that's a relation. Or you can even indicate times, and maybe next term, maybe first term, fourth term, maybe. Okay, so that will be for array relation. Of course, we can generalize it to k-array relation, but the foundation is still binary relation. It can be represented by binary relation. So, for example, I just give you one example. So R on this. So suppose on 3 sets. All right. That's just a subset of Cartesian product of these 3. So in binary, actually, it's a relation from A to B, C. You see the recursive way to define it. So A from B, from A to B times C, Cartesian product. So we can generalize binary relation to multiple relations, to k-array relations. So there are sections in the textbook dealing with the k-array relation on database and applications. I will not discuss it. Okay. Just take a look at them. It's very easy to understand. It's a generalization of binary relation. Really, the most important thing is binary relations. All right. Okay. Just as functions, we can do a lot of things with functions. From a single function, we can generate other functions, or from 2 functions, we can combine them together to generate more functions. We can do the same thing with relations. And I will just tell you 2 important things, actually. Because relations are sets, all operations on sets apply to relations. For example, if we have 2 relations, R1, R2, they propose from set A to B. If both of them are set, we can produce new relation, that's union of these two sets, or intersection of these two sets, and so on. That's very simple. All right. In particular, we can deal with a complement of relations. It says complement of relation. It's very easier to see it in the matrix. You just change 0 to 1 and change 1 to 0. So that's why matrix is very useful and very important. It's very easy to do so, to see the complementary relation. Just 0 to 1. Also fun. Fun. Let me see. Let's see. Do I talk about? Oh, it's okay. It's okay. Yeah. Okay. Inverse apply to something different. Okay. It's okay. Okay. So just change 0 to 1, 1 to 0. And no need to be in a single set. Different set is also okay. Okay. So complement is very simple. Because we're talking about sets. It's a Cartesian product minus our. So it's this set. That's complement. Okay. Now there are two important things about operation relations, or how we can manipulate relations. One is inverse relation. So don't confuse with this one. Yeah, when I talk about this one, I want to think about the other one. We can talk about inverse of the relation. So that's similar to inverse of function. Inverse of function. That's inverse of function. So that's what corresponding to inverse of function. All right. Now, since R is a relation from A to B, the inverse. This one is from B to A. Okay. And the internal matrix is just transposition. So if we have MR here, now the matrix cell is inverse equal the transposition of this matrix. Rows become column and column become rows. All right. So just transpose it. That's the relation. So it will the matrix look like this. The transposition will look like this. 1 0 is still same, but it's just different one. This relation from A to B, but this its inverse is from B to A. Okay. The matrix, the content entity inside the matrix does not change. We locate the matrix by 90 degrees. Just 90 degrees. Just the inverse of relation. Just like inverse of function. So instead of pointing from A to B, the inverse is just the reverse direction of the arrow. So that's inverse. Okay. All right. Okay. I see. Is there a question? Let me see. Yeah, Cartesian product A times B times C, as I explained, it's from A to the Cartesian product of B times C. Okay. Yeah, B times C. Yeah, basically you're right. Okay. All right. Now there are another important notion of called the composition. Just say it's composition of function. Composition of functions. So we have say f1, fx equal to x plus 1, and maybe gx because square root of x, we can combine them to obtain a new function, say 2 square root of x plus 1, for example. That's the composition of these two functions. Yeah. And similarly, we have composition of two relations. It's very simple, but the notation, be careful with notation. Use this function. I'm thinking of two relations. So one relation R is from A to B. Another relation is from B to C. We can combine these together to obtain a relation from A to C. So that's the purpose. All right, it's very important. The first relation is from A to B, and second relation from B to C. So these two must be same in order to combine them together. All right, one good example is say yeah, in connection with a student, say timetable, private timetable maybe. Okay. So each student will have his own private timetable. So that indicates the times for each courses you are taking. All right. Now, actually, there's a combination of two relations. One is a course. Let's say each student takes some courses. So let's say student to course. The first relation is each student, the course you taken. So there are relation from students to courses. And there are another relation, timetable for courses. A timetable, time slot here, so maybe I use S. So here the time slot. All right. So university certainly cannot give you the full table for each student, give a timetable. So what university will do is have this relation. For each course, there are time slots will be assigned several time slots. All right. Now, private timetable for students is just combination of these two relations. It's a combination. So it's a combination of these two relations. Okay. So that's a combination of two relations. Notationally, be careful with notation. There are reasons for it. Notationally, composition of R and S. So composition of R and S. Notationally, we use S small circle R instead of R S. Sometimes you may just see SR without this circle. Maybe some people may do it in that way, okay, or may other notation. But ordinarily, we will write SR instead of RS. Okay. So be careful with this notation. We use in notation this way SR. The reason is we apply R first, then S. So we apply R first, then S. In the matrix, it's become more clear when we talk about matrix. All right. So composition is a new relation that maps. So suppose A belongs to A, C belongs to C. Okay, so an element inside A and an element inside C. Now, whether these two are related or not, so AC belongs to this new relation. So here I will not use infix notation because it looks good, maybe a little bit strange. Just use this original definition. So this here belongs to this relation, just adding function. If and only if there exists a B such that A is related to B in relation and B is related to C by S. So that's the definition. And graphically, what it means actually is very simple. So let's see. All right. So, so here, R relate the elements A to B. So that's R. And S relate the element B to C. Okay. Now this is a new relation. The composition relates the element to C if we can hold from A to C by following this arrow. So one blue arrow, one red arrow. So in this case, indeed, we can do this. Then these two are related. Otherwise, they're not. So that's the composition. So in the previous example, timetabling, so if student take course, so this course and this course, this parting course, 2440 has timetable. So this connection will give you time, teaching time for this course. Today, two sections, two time slots, and Wednesday, one time slots. So you just follow the link in this way. So that's the composition, just the same as function. All right. The difference is multi-values. It can have many. For example, this A will relate it to these three. This one and this one and this one. For function, only one value. Now it can have multiple values. Okay. So inverse is just taking an inverse of function. All right. Now the internal matrix. Internal matrix. Okay. Now again, be careful with ordering. Okay. Here is R first. Then S. In terms of matrix, it's MR first, then MS. Okay, so it's basically follow this ordering. But the first one is Boolean multiplication. So it's a Boolean multiplication of these two matrices. All right, so I believe you know what Boolean multiplication means. Okay, let me just give you a quick example. Okay, so for example, we have these two Boolean matrices. The Boolean multiplication is for this one will give us the value of the first, will give us the value of the first element of the M11. So this value comes from this column, this column. Then if you look at this as a bit stream, so it's bitwise AND. It's bitwise AND. Multiplication is bitwise AND. So this one agrees. So it gives us 1. All right. Actually, that will give us this matrix, I believe. Yeah. Okay. So that's Boolean multiplication. So that's why the matrix representation will be very useful. To compute the computation, we only need to Boolean multiplication. One thing important is ordering. Computation of S and R in this notation is S small circle R. But the ordering when we do matrix multiplication or we use following graphic notation is still from R to S. have to be careful when we deal with it. Actually, this one should be obvious because if the size, the dimension are different, it's easier to tell. If I cannot put this one forward, because this one is 2 times 3, this one is 3 times 2. If I put this one there, I cannot multiply these two matrices because the dimensions are not matched. Right? If I put this one in this way, it's easier to notice mistake if their dimensions are different because I cannot do multiplication. Okay. But the problem is very often when we discuss relation, we'll discuss a relation from a set to itself, from S to S. Very often when we discuss a relation, we'll talk about relation from a set itself, set to itself. Look at these common relations. Less than equal, equality, or this one, all these relations, actually the sets A and B are same. So from now on, I think I will focus on relations on a single set instead of two sets from one set to another. Then we'll discuss a lot of different properties. Okay. So very often when we deal with a binary relation, actually we deal with a single set A instead of two sets. So from now on, we'll focus on such relations. And it will give us a very important subject or object called the graphs. So that will be our subject of next 2 weeks. So from its graphic representation, we'll get this object called the graphs. So which will be our focus for the following next week, last 2 weeks actually, last 2 weeks of the term. Okay, I think that's your question. Let me see if it's related. Oh, okay, all about Boolean multiplication. Okay, I thought you learned the Boolean multiplication. Actually, it's very simple. Okay, so let me say a few words. So when we discuss multiplication of two matrices, the matrix multiplication. All right. So in order to have A times B, the dimension is important. A may be of n times T, maybe then B, T times S. So dimension here is number of columns. Must be the same as number of rows. All right. In order to multiply two matrices, number of columns of first matrix must be same as number of rows for second matrix. Same for Boolean matrix multiplication. The only difference is in determine a particular value, particular integer. So suppose that's for Boolean matrix. Boolean matrix is 0, 1 matrix. Each integer is either 0 or 1. So it's a matrix. The integer is either 0 or 1. Right. The only difference is in multiplication. So suppose C equals AB in multiplication, Cij equals summation of Aik Bkj, right? So k equal 1 to n. That's how we compute integer ij. For multiplication for matrix multiplication. The only difference is for Boolean matrix. This one becomes off, and here becomes end. So that's the Boolean matrix multiplication. So eventual value will be either 0 or 1. All right. So that's the only difference. Here is and. Multiplication become and, summation become odd. That's Boolean matrix multiplication. Okay. But because 3 students asked about Boolean matrix multiplication. Okay. I thought you are studying digital logic. Digital logic, then they should mention the Boolean matrix. But anyway, very often we deal with relations from A to A itself. Then we say relation R on A. So it's easier to say it. Instead of say relation from A to A, we say relation R on the particular set A. Many relations we're familiar with actually a relation on a particular set. For example, less than relation on real numbers or on integers and so on. Less than or equal on real numbers, on integers, and so on. Okay, all these inclusion, set inclusion relation on certain domain or universe. Set relation or certain universe. For example, we can have real numbers or integers, whatever. So subset of integers, subset of real numbers, for example, we can have this relation. Okay. All right. So for example, say 1, 2, 4 is a subset of 2, 4, 5, 6. So that's subset inclusion relation. Okay. So strictly speaking, that one should be power set, but sometimes people just abuse it. Okay, that's including relation. But strictly speaking, it's on subset, on power set. It's a subset. Okay. And this notation should be on subset. But it's understood sometimes. So I kind of abuse it when we talk about this inclusion relation. All right. Okay. Now, once we have a relation on a particular set, then we can talk about some important properties. There are at least four important properties to describe some common features of such relation. One is called reflexiveness. So whether the element is related to itself. Reflective means in graphic representation, it's related to itself for every element. So reflective means for every element of A is related to itself. That's called reflexive. So for in the picture, every element will have a loop. So that's why you can call it a loop. Every element have a loop. For common relation, this one is reflexive. This one is reflexive. Subset is also reflexive, but not. So not reflexive, strictly less than, strictly greater than, or top subset. These are not reflexive. All right. Okay. So I think we'll have a break first, then I continue for other properties. Okay. And then I'll give you a lot of examples to enforce the idea or the concept, main concept of these important properties. Okay. Okay, let's have a break. Thank you.